Okay, so in this problem, we're asked to find the lateral area of a cylinder, maximum lateral area, that can be placed inside a right circular cone. So the first thing that we need to do here is to represent this or illustrate the figure. So I will try to make this as clear as possible. So this is what it looks like for the right circular cone. So I will try my best to illustrate this. Okay, so this is the front view of the right circular cone, and if we try to inscribe a cylinder in this figure, that would look like this. Okay, so let's try doing that one. Okay, so now let's label the parts of this figure. Now I'll be using capital letters for any part of the larger figure or shape, and then I'll be using smaller letters for those parts of the smaller figure. So let's be consistent with that notation. So that's the height, and then for the smaller figure, which is the cylinder, the height is of course the small h, and then this one is the diameter of our cylinder. So basically, if we're asked to find the lateral area or the maximum lateral area, we just have to take the circumference of that cylinder and then multiply that with the height of the cylinder. So basically, if you would imagine this and cut the cylinder vertically, so you'll be able to flatten that cylinder in such a way that this is the diameter and then this is your height. Of course, that's not how it looks like really if you would flatten that, but the idea is that you will try to find the lateral area, which is just the area, the frontal area of that figure. So basically that's simply pi d and then h. So this is our lateral area, and if we need to maximize this, we need to express this d, it should be small d. So if we would want to maximize this, we need to represent this as any variable with respect to the other variable being just one variable. So what I mean is, if we choose d, then we need to express this in terms of h, and then if it's h, then we should express it in terms of d. So either way, that will just work the same way. So now, to be able to find the relationship between d and h with all the variables that are presented here, we should also note that d and h, capital D and h, are constants. So they are constants because we know that we are looking for the largest cylinder or the maximum lateral area of a cylinder that can be inscribed in this right circular cone. So basically, the larger figure is kind of fixed, and then the smaller one is the one that we need to determine. So that's basically why d and h are constant. Now, to be able to relate the small d and h to the capital D and h, so that's basically the cylinder and the cone, let us find the relationship between these triangles that are actually involved in this section. So if you would look at the small triangle right here, so this triangle is basically the diameter of this cylinder, and then at some distance x or y or any distance, and then there's this large triangle or this in this front of the cone. So you can see it right here. So basically they are similar triangles, and if they are similar triangles, so we can just do some similarities for this. So by virtue of similar triangles, we know that if we have the diameter over the height of the larger triangle, we know that this is also equal to the diameter of the smaller triangle, and then right here we know that this height is actually the larger height of the cylinder, the cone, subtracted with the height of the cylinder. So I could just write this as h minus small h. So with this, I have already related d with respect to all the remaining variables and constants. So if I would be writing d, I could just write that as d over h and then h minus h, small and capital. So I can now rewrite this in terms of the constants and one and a single variable, independent variable. So that's pi, and then d h, and then h minus h, and then times h. So these are the equations that we actually combined or represented in a single expression, such that we have one independent variable. So as you can see here, you might be noticing that I have actually three letters, or four if you include pi. So remember, the and h are constants, as well as this h. So basically, if h, the small h, is the one that we need to determine, so this expression has actually one independent variable that is being evaluated. So in that case, I need to differentiate this lateral area to be able to get the maximum lateral area. It should be differentiated with respect to the smaller, or the height that is being determined. Because if we would differentiate that with respect to h, then it makes no sense, because h or d, these capital letters, are actually constants. So if you would like to differentiate them, then you would just be getting 0, and you won't get any solution for this. So before we differentiate, let me just probably distribute this so that we can eliminate or factor out those constants. So basically, this pi d over h capital are constants, because as what I've mentioned before, this is kind of fixed because they are the larger value and you're inscribing something on that larger figure. So now that I've eliminated or factored out the constants, I would just have to take the derivative with respect to the independent variable, which is our h. So that is the derivative of the lateral area with respect to h. This can also be rewritten as a prime sub l of h. I think this is the one I used to write before. So it could be represented like this, and then just copy the constants and then take the derivative of this expression. So knowing that this is the independent variable, so the derivative is simply h and then minus 2h. Okay, so this, we have this equation, and then we need to equate that to 0. So we have pi d over h, and then h minus 2h, that is equal to 0. Knowing this, we could get the value of our h, that is simply equal to 2h is equal to capital H, and therefore the height of the cylinder for the maximum lateral area would give us the value in which the height of the cone would be halved. So in this case, for any value of height of the cone, you just have to take 1/2 of that, and that will be the maximum lateral height. The height of the cylinder you need in order to maximize the lateral area. So it is not yet complete, so we need to find the diameter of the cylinder. So if you look here, we know that this is the expression of diameter, so let's go back with that. So that's d over h, and then h minus, we know that h obtaining from this expression, the small h, is actually the capital H over 2. So you could just from this you could just substitute that, and then we have d is equal to capital D over h. We have 1/2 h, so we cancel h, and then we're left with d over 2. So basically, the diameter of the cylinder would always be 1/2 of the diameter of the cone. So it is also equal to the radius of this particular cone. Now for the lateral or maximum lateral area, we know that it's always pi d and then h. So upon substitution with our values here, which are represented as constants, or with respect to the values of our capital H and R D, those are the dimensions of the cone. We have pi, and then d here is actually the radius, and then h would be the height of the cone and then divide by 2. So we could just have any lateral surface area of a cylinder with respect to the cone that is circumscribing it. So that is simply pi r h over 2. So this is the lateral or the maximum lateral area. So the final answer would be actually this AL max, not this one actually. It's just the dimension. So for example, if you have a radius that is equal to 5 and then a height a diameter that is equal to 5 for the cone and then a height of 10, so the maximum lateral area would be that it's 2.5 for R, and then H would be, of course, that is just equal to 10, and then you just divide it to 2 and then multiply to pi. So that's our maximum lateral area. Okay, so that's how simple it is for this kind of problem. But the one thing that makes it difficult for any kind of problem that involves geometry is this: finding the constraints from the figure itself, because it's easy for you to understand that by virtue of similar triangles, but were you able to see that alone by just looking at the figure? So that's the question that you need to ask yourself, because in order to identify the relationships between any of the variables that are presented in your figure, you should be able to see how it looks like on the 2D or the 3D plane, because that's where will you be getting your relationships. It could use something like similar triangles. It could be using the Pythagorean theorem or any diagonals or any relationship that might be existing in the universe of geometry. So I think this is where things really get complicated in finding the relationship. But all in all, if you've already determined that and then you need to differentiate, that's just a piece of cake. Okay, so you can also try to check on the second derivative and then substitute this value. You will be also getting a negative answer for that, which makes this the maximum. Okay, so if it becomes 0, the first derivative test will always suffice for this. So the first derivative is this one. So if you substitute values like, for example, this is h over 2, so at the right of this h over 2, that's because it's 0.5, so you just use 0.4h. Substitution to this would probably, I think it will give you a positive answer. And then if you would be using a value that is greater than this, so let's say 0.7h, so in this case that would be negative. So that makes the number line for this case being something like h over 2, and then we have positive here, and then that's negative. So basically that makes that the maximum for this problem, and you can check that by your knowledge in extrema of a function. Okay, so that's it for the this problem.